with the mic, but I want to see if this is going to cause.
So 7 years ago, our forefathers brought forth upon this nation,
That one is on.
upon this continent, a new nation.
That's the problem. This one is also on.
Anybody else know this? Conceived in liberty. All right. Friends, Romans, countrymen, lend me your ears. I come to bury Caesar, not to praise him.
You're really you've memorized a lot of that. That's great.
The evil men do lives after them. The good is often turned with their bones.
Can the online people hear now? Are the online people able to hear?
So let it be with Caesar.
Are you getting a text? Can anybody online hear? Yes.
I got it too.
Oh,
Okay, thank you.
good. Okay.
Okay. Am I good? Yes, okay. Good morning, I'm Srinivas Sakala from UNC Charlotte. I'm a little out of breath because I just ran in. So I'm sharing the session and my respondent coaches are Ken Elimelech, if I'm pronouncing the name correctly. He's a postdoc at Rice, working with Lydia Kavraki and Moshe Varti, and he works on task and motion planning and planning under uncertainty. And my second respondent co-chair is Everton Vieira from Rutgers, and he's a postdoc at DIMAX with Konstantin Mishchaikov, and his research interests are in topology applied to dynamical systems. So we have 4 speakers today, and our first speaker will be Sihui Li. Please come on down. So she's a PhD student at the Colorado School of Mines, working with Neil Denton, and her focus is on motion planning.
Hello, everyone. So here I'll present our paper. Okay, so motion planning plans a path from start to goal. A complete motion planner will return a path if a path exists, or it will tell you that a plan does not exist. But this property is very hard to achieve for high-dimensional motion planning problems. So people usually go for weaker notions of completeness. For example, widely used sampling-based motion planners are probabilistically complete, meaning that they can find a plan given long enough time, but it cannot tell you whether the plan is feasible or not. So in this paper, the focus is to tell you this infeasibility information along with a sampling-based motion planner. So before we get into more detail, why is knowing this infeasibility information important? Going from lab settings to real-world scenarios, motion planning is oftentimes a sub-problem to a larger problem. So if we don't know whether the plan existed or not, sometimes we face this dilemma. For example, with sampling-based motion planner, if it does not return plan, should we give it more time to plan, or should we try out a different task plan? Right. So without this infeasibility information, it will cause the larger plan to be incomplete or take a longer planning time. So here's the flow of this presentation. We will start with problem definition, then go to algorithm, then focus on the convergence analysis, then end with experiments. So first, our problem definition is a general motion planning problem setup. We have a configuration space a start configuration and a go configuration. The output is a plan if a plan exists, or an infeasibility proof if a plan does not exist. So what is an infeasibility proof? If every path connecting the start and the go has to go through some obstacle region, as is shown in this figure here, then the plan is infeasible. Right, so as is shown in this figure here, we have this loop closure that exists in obstacle region and separates start and go. So formally, we define an infeasibility proof as a manifold that satisfies these three requirements. So first, it is closed, then it exists entirely in the obstacle region, and it separates the start and the go. Right? So next let's go into the algorithm. So this is previously published in our other paper we'll briefly talk about here. So the algorithm has two main threads, the planning thread and the proof construction thread. The planning thread runs a sampling-based planner. Here we are using probabilistic roadmap, and it terminates the plan, terminates the algorithm, it defines a plan. And at the same time, it saves all sampled configurations, both in obstacle region and free space. And for the proof construction thread, it has two main threads, two main steps. Learn a manifold and then validate a manifold. For learning the manifold, we set up this classification problem where one class is all points connectable to the goal, and all other points are the other class. And we learn a classifier. So as you can see in this animation, as more points are sampled, the manifold converges more and more into the obstacle region. And here we are using radial basis function kernel support vector machine. We are using SVM because it gives us an analytical form boundary function along with other benefits. So after we learn the manifold, we validate the manifold. We do this by first sample points on the manifold and then triangulate using the sample points with tangential denali complexes. And then the result of this triangulation is this polytope shown in green here. And then we check each facet of the polytope to make sure that is contained in the obstacle region. So that's the algorithm. Next, let's go into the analysis part. So as you can see in the algorithm, we first learn the manifold and then validate the manifold. So all the rest of the step actually based on result of the learning step. So then here a question we want to answer is, if no plan exists, then will the learned manifold eventually converge into an infeasibility proof so that the rest of step would follow? And how fast would that happen? So in this paper, we prove that if no plan exists, then the probability of the learned manifold being an infeasibility proof converges to 1 as more points are sampled. So to prove this, we basically need to prove that the learned manifold follows these 3 requirements of an infeasibility proof. That is closed, it exists entirely in the obstacle region, and it separates start and go. And this last statement is obvious since we're learning a classifier. This first statement will be natural after we prove the second one. So the key here is to prove that the manifold converges into the obstacle region. And to prove this, we identify regions that need samples and then calculate the probability. So here is the idea of this proof. We first identify this region that needs sample, and then if there are points in this region, it will push the manifold into the obstacle region. And here is more detail of the proof. We identify this region along the obstacle region boundary, and then decompose this region into this smaller, we call RI regions, such that if there is at least 1 point sampled in each RI region, then the manifold will exist inside the obstacle region. So if we are using uniform sampling, then the probability of failure, that is the probability of with at least one R region with no sample, can be calculated eventually with this number here. That is, inside the parentheses is a number smaller than 1. So as n, the number of samples goes to infinity, this probability of failure converges to 0. So the probability of success, that is probability of at least 1 point in each RI region, converges to 1 as more points are sampled. And as it turns out, we can put a tighter bound on the probability of failure by using binomial distribution. And applying Chernoff bound on binomial distribution gives us that probability of failure is eventually bounded by this negative exponential term with respect to the number of sample points. And this gives us our second result. That is, the probability of failure decreases to 0 exponentially.